Example 3, population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% over the next 4 years. What exponential function models the population of the city over that 4-year period? If the population continues to grow at the same rate, what will the population be in 2040? So first off, this is only considering data from 4 years only, but we're going to create this model that is going to be for predictive purposes. If this population continues to grow at this rate, we're going to see that there's going to be some end population. And a couple things we're going to do in this problem, it's going to happen quite often when we start doing real world stuff. When you start to deal with very large numbers, or when you start dealing with years, like the year 2010, the year 2015, stuff like that, you're doing predictive models. It's important that we construct something that's easy to work with, but also gets us the information we're looking for. All right? And what I want to show you is the basic structure of an exponential function is some number equals some number times some number to some power. That's the basic structure of an exponential function. All right? So a sub n, a sub 0 both represent numerical values. B is some constant base value, and t is some power. All right? That's the basic structure of an exponential function. Your b to the t power creates the exponential part of it. It can be multiplied by some constant, all right, to create some number over here. That's your basic structure of any exponential function. All right? And in this case, I'm trying to model population growth. I need to start off with a certain population, end with a certain population, and there's a growth rate or decay rate of population. That's what goes there for b. And you know what? I'm going to put a sub 0 instead of a sub n. Usually we start off with something. So a sub 0 usually is what we start off with. A sub t is what we end up with after some amount of time. All right, so when I'm looking at this, it says it grew. Okay, grew means to get larger. Okay, so when you deal with exponential functions, they either, as you go to the right, they either go up, which means they're growing, or they shrink and they lower and flatten out to 0, right? One or the other happens. They either grow or they decline, which is also called decay. And it tells us the rate of growth is 1.3%. All right, so you always consider 100% to be normal. Okay? If something stays the same, it's got 0% growth, 0% decay. That means each year it's the same amount. So it's 100% of what it was the previous year. If there were 50 people, the next year there's 50 people. The next year there's 50 people, and so on. That's no growth rate, no decline. It's just the population stays steady. All right? If there's growth or decay, we're going to modify 100%, either bigger for growth or less for decay. So in this case, we're growing 1.3%. We're going to add to 100, so we end up with 101.3%, or 101.3% for the actual value we're going to put in our formula. All right? So there's 4 pieces of our formula. We have a sub 0 equals something, a sub t equals something, b equals something, and t equals something. All right, what b equals is the percent, but we want the percent as a decimal. We want b to be a decimal number, not a percent. So if 101.3% is the amount the population is growing each year, 1.3%, so it's 101.3% more each time. So we're going to get 1.013 is the decimal version of that percent. Slide the decimal point 2 spaces over. If this problem happened to say the population was declining 1.3% each year, we'd be subtracting 1.3%. We would have got 98.7, so 0.987. So there's always some decimal here for b that represents the rate of growth added to or subtracted from 100%. A sub 0 is the initial fact. In this case, we're dealing with population. So the initial population was 4.6 million. Okay. Now, in order to keep numbers smaller, they do this quite often. Instead of putting 4,600,000 people, they're putting 4.6. And they're saying that's millions of people. So if the answer comes out to 5, that's 5 million. If the answer comes out to 23, that's 23 million. If the answer comes out to 0.1, that's 0.1 million, also known as 100,000. So again, instead of having to put 4,600,000 in our formula, we're going to put 4.6 in our formula. Okay, when I'm making an exponential function model, okay, one exponential function models this, what I'm looking for is I'm looking for t and a sub t to be unknown values. And I'm looking for a sub 0 and b to be known values. So once I know what these two things are, I'm good to go. Now, I do want to identify what a sub t and t represent. And a sub t is going to be the population in millions after t years. And t, the year 2010 is the starting of this problem, right? So this population, 4.6 million, happens in year 2010. I'm going to say t equals 0 represents 2010. Okay, when I'm making a model and there's a year involved, I don't want to put the year into my equation. That makes it hard to deal with. So I'm going to let the very beginning year be year 0, and any number beyond that's going to, like, if I want to know the year 2017, how many years is that past 2010?
7.
So t would equal 7. If I know t, if t is equal to 5, what year would that be? 5 years past 2010 is 2015. So I want t to represent how many years beyond 2010, instead of, like, when they say year 2015, I don't want to have to put 2015 in my formula. I want to keep my numbers small and easy to work with. So the formula I'm going to get here is going to be a sub t equals 4.6 times 1.013 to the t power, where a sub t is the population in millions, and t is the number of years after 2010. When they're asking you to create an exponential model, create the equation and then define what the variables represent. Have the reader of the problem know exactly what these variables represent. And again, if there's some kind of deal like what's the number of millions of people, if I just put 4,600,000 here, then A of t would be the population. It would already be in millions, but I'd also have bigger numbers to deal with. So it's kind of a pick your poison type moment there. Either you got to describe this thing or you have to deal with large numbers. I prefer to describe what it is. The other part of this problem, if the population continues to grow at the same rate, what will the population be in 2040? How many years beyond 2010 is 2040? 30 years. So they want us to use this equation we just created, let t equal 30, and figure out what the population is going to be, right? So I'm going to come over here to my calculator, and to do part B, I'm going to say the population after 30 years is going to equal 4.6 times 1.013 raised to the 30th power. The subscript is t. So if you say a sub t, it's not wrong, but officially a sub 30 is what we're finding here when we let t equal 30. And my calculator can evaluate that for me. So 4.6 times parentheses 1.013 end parentheses caret 30. So this is raising 1.013 to the 30th power, multiplying that number times 4.6, gets me a population of 6.78. A sub 30 is equal to 6.78. What does that represent? 6.78 what? Million people, right? So 6.78 million people would be the approximate population of this particular town in 2040, assuming that the growth rate remains constant throughout that entire 30-year period.